Welcome everybody. Welcome to our second session of the day that specifically focuses on the use of AI. I'm delighted to be back with you and to have you back with us. The session that I'm very happy to introduce to you now, we're going to be focusing on AI and data science. But before I come to that, I just want to remind you of a couple of features of our digital conferencing system. The first one is that if I can get that right, to that side of your screen, you'll see that there's a place that you can put questions and answers, or you can put questions and we'll try and give you the answers, questions for our speaker, Ala Tarighati. And you will also see various other features. Top right of your screen, you can choose to expand the view. It will hide the Q&A box, but it means that when Ala shares his slides in a couple of moments with you, you'll be able to go on seeing Ala's video and seeing him presenting to you. The session that we are about to listen to from Ala Tarighati is AI and Data Science Applied, building and maintaining a model production pipeline at SEB. Ala Tarighati, we're very lucky to have him with us because he is a senior data scientist, has the practical experience of applying AI, a lot of talk about AI, but actually hearing real life uses is another thing. And I think we're going to learn some interesting things about how we can get more out of the reams of data that we all hold. So over to you, Ala, and thank you very much.
Thank you, and welcome everyone. I'm very happy to be able to present this conference. I would be even happier though to be doing it physically, but anyway, welcome anyway. And I'm going to share my screen now so everyone can see my slides. Wait a moment. So I hope it's working now. Yeah. So welcome to this talk again. I'm going to talk about AI and data science here at SEB, and also talking about how we build and maintain a model into production. SEB actually is a bank which was founded in 1856 by Wallenberg families, and they are still the main stakeholder or shareholder via investor AB. Later on in 1972, the bank merged with some other Swedish bank, and SEB or SEB Banken was established. Here at SEB, we have different types of clients, like large corporates and financial institutions, like small and medium-sized entities and private clients. And also we are well positioned to serve corporate customers basically all around the world. We have branches in about 20 different countries, and we want to actually be where our clients are and also help our clients to have a good customer experience and to get a good customer service. To do that, we have different types, or we have had different types of initiatives in the bank, mainly AI and automation related initiatives to help our clients. You can see some of them between 2016 and up until beginning of 2020. So as the topic of the talk suggests, I'm going to talk about AI and also putting models into production. So let's start with a definition of what is AI or artificial intelligence. I am actually borrowing a definition from John McCarthy, who is known as the father of AI, and he defines it as the science and engineering of making intelligent machines. In other words, any task performed by a program or a machine that if a human carried out the same activity, we would say the human had to apply some intelligence to accomplish the task. But let's pause here, and since I'm a data scientist, I am more interested in like the area of AI which is related to machine learning. So I want to change the gear and more focus on machine learning models and also putting machine learning models into production. I'm sure in different areas of AI, you can use the same principles and practices that I'm going to present for specifically for ML and use them for different types of AI applications. So what I'm going to talk about is the machine learning and traditional programming, elements of machine learning application, machine learning specifications, and machine learning models to production steps at the end. So let's start with a definition of machine learning. What I mean with machine learning is actually, again, I'm borrowing from some pioneer who popularized the term machine learning, Arthur Lee Samuel. He was a pioneer in the field of computer gaming, and he defined it as the field of study that gives computers the ability to learn without being explicitly programmed. So as you can see here, we have some keywords which are like computers, programmed, and also learning. So from here, we can have some like a feeling that there might be a lot of things in common with traditional programming when we are talking about machine learning. And that's a very good sign because we can use a lot of experiences and also a lot of things that we learned from traditional programming to apply on machine learning models and to build and maintain like machine learning pipelines. So let me talk a little bit what is the difference between traditional programming and machine learning. In a traditional programming, we have usually some sort of similar structure. We have on the left-hand side some data. Let's assume each plus in the left-hand side like plot corresponds to one client, and we let's say collect two different like features of each client, x1 and x2. x1 might be like client activities, and x2 might be, for example, their credit. Each plus corresponds to one client. And then in a traditional programming, what we do is that we already know some rules, how to classify our clients, how to divide our clients, or solve some problems that we want. And in some way, we predict the behavior of our clients in the future. So we apply the rule that we already know, we program it, and on the right-hand side, we get the answers. You see that the curve I showed on the top is the rule that we know beforehand. Then, for example, we can say the red plus corresponds to clients that are going to churn or leave the company, or it can be like any type of company or institution. And then the ones below the curve correspond to clients that are not going to churn in the near future. What this plot suggests is that in the traditional programming, what we need to know is the rules. We need to know which rule we are going to apply. And also we need to be able to program the rule that you want to apply. So this might not be always easy. For example, if you want to do some like classification of images between cats and dogs, if you want to have like a face recognition, then it might not be easy to knowing the rules and also being able to program the rules. So then in this case, machine learning can come into play and help us in finding the rules and also the programming the rules. So compared to the traditional programming, for the machine learning approach, we have something like this. It's like a two-layer, like a pipeline. First, on the left-hand side, we have some historical data with answers, and then we apply some machine learning model, which the output of this machine learning model will be the rules that we're looking for. So you can see that we don't explicitly know the rules, and we use machine learning model plus historical data to get these rules. Then we can apply these rules, do the same pipeline as we did for traditional programming, and then get the desired responses. So what this implies in the first, like when we see it, is that when we are using machine learning approaches, there are these approaches or applications are subject to changes in three different axes. Not only code, which is common between machine learning models and the traditional programming, but also model might change, and also the code might change too. So by data, and the data might change. So it's like not only code, but also data and model. Code might change because the business need might change. They might also we might also find some bugs in the code, and we need to change the code. Model might change because it is very common that we find better algorithm, for example, like more state-of-the-art approaches, neural networks that we want to apply on to our data. So we need to change the model or algorithm, and also the data might change because at some point we might start getting other types of data from our clients or from market out there. So we need to think about these 3 dimensions that we have, or these 2 extra dimensions compared to traditional programming when we talk about like AI in production. The very first thing it's going to imply is that since we have different types of like changes and like dimensions, let's say, in our pipeline, we need different types of competences. We need data scientists who are able to build these models, find a good algorithm. We need data engineers who are good in like transferring data between different systems, and we need machine learning engineers who are capable of like finding a good way for implementing the model into the production. I'm gonna get back to this one, but this is not the only thing which differs between machine learning models and traditional programming. So if you ask your data scientists of your team to do some project, you might give them some sort of, let's say, the historical data and a problem. They might go and do some designing stuff, hyper-tuning of parameters, and then at the end they come up with very good machine learning models. The machine learning model that they come up with, they usually consist of pre-processing codes and machine learning train and inference codes. I'm sure a lot of data scientists in many organizations are capable of doing very state-of-the-art machine learning projects, finding really good results using by this pipeline, and the output as a machine learning code will be something really good in most of the times. However, when we look at the whole pipeline for building a machine learning system, this machine learning code that your data scientists are going to deliver is just the tip of an iceberg. There is a nice paper under the title of Hidden Technical Depth in Machine Learning Systems. They explain the other components of a full machine learning or real-world machine learning system. As you can see, the machine learning code is just a tiny bit, with all due respect to all of data scientists, in the middle. And we have a lot of different components like monitoring we need to take care about, like analysis tool, for example, data collection and configuration. So the real challenge of a real-world machine learning system is not building a machine learning model using your data scientist. That's a very important part, but it is not the real challenge. The real challenge nowadays is to build an integrated machine learning system and to continuously operate it in production. But how we can do that? The good thing is that since there are a lot of similarities between software development systems and machine learning systems, then we can probably borrow a lot of principles and best practices from software development, and hopefully we can tweak it, find a way of doing it for machine learning models. In software development systems, DevOps is a very popular practice in developing and operating large-scale software systems. In the left-hand side, you can see a lifecycle management of according to DevOps. You can see they have code, test, deploy, like monitor, and so on. And for each of these parts, there are a lot of good softwares and apps are out there that you and your team can use. Also, there are like important practices when you use DevOps, like continuous delivery, continuous integration, like continuous deployment, and so on. But how can machine learning use these type of principles and practices? So what we feel now is that for develop and operate complex machine learning system, we can use and apply these DevOps principles. However, with some considerations, we saw already some of these considerations, like involvement of different parts in a machine learning or like a system team. But I also found a couple of more probably interesting specifications for machine learning systems. So in the right-hand side, in the bottom right, sorry, you can see I listed 5 of them: team skills, development, deployment, production, and testing. These are some of the main machine learning system specifications. The first one, if we want to talk about the team skills, we already said that the teams of machine learning systems, they also include data scientists. They do exploratory data analysis, model development, and experimentation. And you should also know that they are usually not experienced software engineers. So while building a pipeline for machine learning systems, it's good to think about those people as well to make their job or life easier. The other difference or a specification for machine learning system is that machine learning tasks are usually experimental in nature, in the sense that your data scientists might go try different features, try different algorithms and parameters. We also need a way to track what worked and what didn't work, because in the future, we are not gonna try and go back and redo what already didn't work. So we need a way to track these stuff as well. In the deployment phase, we need to also think about some other stuff. We are talking about machine learning models, and training machine learning models. So we need to retrain models, we need to version the models, and also since we want to be reproducible, we want to have a reproducible model, we also need to version the data, because each model or algorithm is in some sense bounded to some data set that we say this model gave this performance when we applied it on this specific data. So we need to also version not only the model, but also the data. And you can see that the pipeline, it adds a lot of complexity also for deployment. When you go to production, you need to also think about the performance of your machine learning models. Usually, these type of models, the performance of these models decays not only because of suboptimal coding, but also because of the data evolution. What I mean is that when you train a machine learning model, you usually use some historical data. And we assume that the behavior and the underlying behavior of the historical data is similar to your real-time data. So if the distribution or the nature or of these two are not the same, or one of them changes in terms of distribution, then your machine learning model might not work as expected. For example, if we have had a model which we trained 2 years ago, we didn't have any COVID stuff happening, but nowadays, if we apply the same model on real-time data nowadays, we need to think that, oh, the underlying data they don't have the same behavior or the same distribution. So we also need to track statistics of online data. We need to monitor the performance of the models. Once the performance is below some threshold, we need to retrain the model. And then last but not least is the testing of machine learning models is more complicated and more involved. And the reason is that we have more parameters to take care of, like a data, like training the model or the inference model. So all of these shows us the machine learning model might be somehow very complex and complicated when you want to put it into production. But let's jump into the last part where, considering all of this stuff, I want to tell you about machine learning models into production. But before moving to that part, I just want to note that when we compare MLOPS and DEVOPS, we have a new component, which is CT on the bottom of this slide, which is about continuous training. And here we want to have a whole pipeline which takes care of automatically retrain and serving the model. So keeping this stuff in mind, we are going to one of the first pictures regarding machine learning model to production machine learning models that I showed you how this works in somehow very naive way when you have to ingest the data, both for training the model and also for serving the model. You need to train a model using historical data. You need to extract model parameters, which parameters you use for tuning, what was the performance of your trained model, and what you can expect actually from this model. And then we have the model serving when you put your model into production, for example, using some as a REST API or app or some application or I don't know, something like that. And finally, you do the prediction and get results out of this model into production. So considering all of these steps, I showed you in a kind of naive way The level of automation of these steps that I showed you actually defines the maturity of the machine learning process in your organization or in your company or whatever. So keeping this in mind, Google, they have a paper that I will show the name of the paper, like in the bottom left, MLOPS, continuous delivery and automation pipelines in machine learning. They explain in their paper 3 different layers of MLOPS. The first one is the manual process, where you do the transitions between different steps are usually manual. What do we mean with this manual process is as follows. Considering the dashed line in the middle, you can see on top of the dashed line, we have experimentation zone where your data scientists are working. They do their data science experiments and so on. And below this dashed line, you have the production zone when we deploy the model into production. In a manual process, your data scientists, they do their job, experiments, and they train a model. What they deliver is actually a trained model in some format like pickle or I don't know, something in some way. And then they put the model in some model registry. Then it is your data engineer and your machine learning engineer's task to create a continuous delivery and then start using the model, then serve the model and also do some monitoring in your model. And once the performance decays, it goes below some threshold, then you need to tell your data scientists to ingest data, do their job again, train a model, and then do the whole pipeline again and again in a totally manual fashion. So as you can see here, there are some rooms for improvement. In the level 1, in order to handle this situation, what they suggest is that data scientists, instead of giving the final model, they give some source code that they came up with. And then your data engineers or machine learning engineers, they put the source code into the production. So you have a continuous train pipeline that you can use, and whenever the performance of your model goes below something, some threshold, then there is a automated trigger which makes this continuous train part to do a new train or train new model using a more fresh data and put the newer model into production. So you can see here that you don't need data scientists all the time, train model with new data, and then do the manual task and giving and then the manual task for the transitions between different steps. However, the drawback of this type of models is that it's good if you have a couple of models and you want to train them regularly with new and fresh data. But what happens if you have a lot of different machine learning models? If your data scientists want to train and try different ideas, then this is not going to be the most efficient way. And the drawback or the bottleneck actually here is the deploy part on top right hand side. Then Google suggests to create an automated CI/CD/CT, where you create an automated pipeline or CI/CD pipeline in the sense that just using the source code, that this pipeline is going to create the packages, whatever is needed to deploy into the production. So you don't need anyone, any manual transition between different steps. Different companies, different organizations, they are using different levels of this MLOps. Here at SEB is the same. I can say for different projects, we have different levels. Not all of the projects we have in production are level 0, not all are in level 2. We have a combination of different things, some more sophisticated in terms of machine learning, we go with level 2, some, less sophisticated, we go with more advanced MLOps, and some more sophisticated. So we are in the stage of level 0 or level 1. For each of these parts, there are multiple applications or apps that you can use. Here are some suggestions. Actually, these are the apps that we here at SEB use to put our models into production. And I wanted to share with you what are different apps. or applications or softwares that we are using for each part of this like automated pipeline. And last but not least is about if you want to go to production, if you have some machine learning model or some data science projects you want to push into production, you need to think about some of the tests. There are like nice papers out there. You can go and there is a paper, I think, what is your machine learning model score? There you can find a lot of different tests and a lot of different kind of questions that you need to answer before thinking about putting your model into production. For example, what to monitor, how to monitor your model, and how much it costs, and should we use a simpler model or not? And these type of questions, I think you can find a lot of good information out there on the internet, but just think about it before you go into production. So that actually concludes my presentation, and thank you for your attention.
Well, thank you, Ala. That was very interesting, and I wonder if you wouldn't mind taking the slides off the screen, and then our guests will be able to see us as we're talking. I thought that was very interesting. We've had a question raised by Toby Torsland, who wants to know how you can vouch for code integrity when you use AI. In other words, how do you analyze legacy and new code continuously to make sure that there are no vulnerabilities, suboptimal code that would compromise the data?
Yeah, I think that's always a valid question, because as I said, we data scientists are not like experienced software engineers. I think in that sense, that case, there are a lot of good practices that machine learning engineers can bring. I think having machine learning engineers, those people that they understand the model and also they have good understanding of software development, I think they can help with this stuff a lot. But that's always a valid question. We try to do it like iteratively, making it better and better. Yeah, I don't know if there is like a clear answer to this question.
I guess that there are a couple of inherent hazards of the process. One of them is building your bias into your data schema, in a sense. If your assumptions around the way that you organize the data may drive the outputs. I've certainly seen that with trading algorithms, where you organize the data, you're almost bound to get the answer that you assumed in the first place. How do you control for that?
For that one, as far as I know, there are like data stewards. They are different like people like dedicated to make sure that like the schema of the data, what we expect from the data, how different databases are connected to each other, if this is always valid or not, like the document stuff, that is something going on. And I think that's very important, because if you don't know exactly what your data is and how it is organized, then basically you can't do anything. That's the very basic, like a first step of doing like machine learning or AI in your organization. But at the same time, we have some data lake in place, and where the idea is to put all the data we have in some like centralized place. There are some multiple, let's say, solutions for that we use in the organization, but it is also ongoing, ongoing work, especially if you have this legacy, if your company is not new, you had this stuff before. So there are works, I know that there are a lot of works around it. Yeah, this you just need to accept it and try to fix it.
So you talked about three legs right at the beginning. You talked about the data schema. You talked about the model, which is the algorithm. But you talked about where the business starts, which is what's the business outcome that you're trying to deliver. And again, from my own experience, very often there would be a quant who would they'd use appropriate statistical tools to come up with hypotheses. They'd write a PowerPoint, and the coder would then code based on that PowerPoint. So you're actually already at two removes from the data modeling in a way. And how do you control for making sure that what the coder codes is what the business intended, rather than something getting lost in the translation of setting out the requirements?
Okay, so I think so I didn't put like all parts of like teams when we are doing a data science or machine learning project, because I think the very important like player in this project is someone who like has an understanding about the business requirements and also has some technical understanding. We usually have a lot of these type of like meetings where we try to understand each other, what you are looking for and what I can provide you. So that's a very important part of any project. And I think it's very important to have like to define small steps and build on top of each other. So if there is any misunderstanding, so we can fix it right away or very fast, like every 2 weeks or every 3 weeks and so on. So this is very important to have someone who understands both of them, or to have a good communication.
Yeah, I would say from my own experience, this is exactly an area where having a very DevOps or a very Scrum-based approach, so that you don't lose things as you pass them down the waterfall, is critical. Alec, it's been very, very interesting. I told you offline before we started that this is a subject very close to my heart, so I'm very grateful. We now move into a break. I would invite you to visit our stands, our sponsors, but also go into the meeting hub and you can meet other delegates, other speakers, and also our sponsors. And then after the upcoming break, we'll finish the formal part with a panel discussion with a range of practitioners and vendors looking at some of the challenges of DevOps implementation. Thank you very much, everyone.
Thank you so much for giving us the opportunity to talk about what we are doing and sharing this stuff. Thank you so much.
Thank you.